which is pretty rad, you know. It's a little less rad when you have like 4 hours of meetings scheduled for your day off, but you know, you can only do what you can do. All right. So let's start by taking some questions from the previous assignment. If you guys want to find your work for this most recent homework 6, we'll take some questions from that before we get rolling on some new stuff. Grace, 19? Okay. All right, so I'm going to start by doing like the prime factorizations. I'm not going to draw the factor trees, though, just in the interest of time. So 24, or negative 24 is negative 1 times 2 to the third times 3. 45 is 3 squared times 5. And 75 is 5 squared times, negative 1 times 5 squared times 7. And I'm just going to think about that like all under one radical. Is that okay so far there, Grace? So negative 1 times negative 1 is just going to be positive 1, so I can just kind of discard those. You good there?
Yeah.
Okay. The 2 to the third is just going to become a regular 2 outside of the radical. I have 3 times 3 squared. That's basically 3 to the third. That'll become a regular 3 outside of the radical. And then I have a 5 and a 5 squared. That's a 5 to the third. So that can become a regular 5 outside of the radical. That leaves me with just the 7 left. And if you wanted to, you can multiply the 2, the 3, and the 5 together and call that 30 cube root 7. So you notice there I've kind of compacted some of the work that we had done before, just to make life a little bit more convenient and not having to write down a million steps. But ostensibly, all I did was build out the prime factorization for everything, think about it all under the same radical, and then group together the packs of 3 and then pull them out front. And anything that couldn't go into a pack of 3 got left on the inside. And then I just multiplied the stuff together. Is that okay? And that's a little bit more, we're still doing the same thing. I'm just kind of documenting it in like a more compact way after you've had a chance to like understand what the process is rather than starting at this, which is kind of confusing if you don't already understand what it is that we're trying to do. But that's a heck of a lot less writing than probably we're doing for a lot of these problems. But that's okay. Like, I wanted you to write a lot here the first time through so that when we start compressing the work, you're able to kind of fill in those blanks in between, right? What else do you guys want to talk about? That was 19. Do you want to talk about some more? How many of us took my advice and like made sure we did at least 10 or 15 minutes of the homework on these nights in between? If you didn't, really strongly encourage you to start doing this and not just waiting to try to do it all at once on Sunday. It makes a heck of a difference if you're doing some of the work in between these days. So when we come to class and want to ask questions about stuff and like you have questions to ask and we can get things addressed and like we can correct errors before we start the next lesson and be able to more fully participate, and it just makes life a lot easier. We had talked about this last week or the week before, I don't remember. It all blurs together after a point. I've gotten about 10 total hours of sleep this week because of my daughter is going through some demons right now and not wanting to sleep a whole lot, and so it's all blurred together into one like tired, messy week. So I'm not really sure when we had these conversations, but I know we did, and you guys remember, right? It doesn't probably matter when we had it. Okay, last call on these. If there's anybody else that wants to ask about the homework from last time. Okay, if you guys change your mind, we can always come back and look at it, later. It doesn't matter. But if we're done with that for today, that's okay. So today we're going to kind of continue talking about like how we simplify these radical expressions. What's up, dude? Okay, did you check in at the office? Okay, just double checking, man. No big deal. NBD. All right, so last time we talked about reducing radicals, and we talked about multiplying like radicals. Today, what's up, my man? Did you check in at the office?
Yes, sir.
Okay. We're going to talk about addition and subtraction and division. Actually, we'll do division first. And we'll see if there's more. I'm not sure. We'll see how long that takes and how we're doing. Everybody cool with that plan? So again, just trying to connect what we're doing to last time since we're just kind of continuing on the discussion. I want to make sure that those ideas are all kind of connected together. But like last time, I'm not going to do any like theoretical. I'm just going to kind of do some examples and talk our way through things. Okay? So we're going to do division first, I guess. So we'll talk about division of like radicals. When I say like, I mean a square root with a square root or a cube root with a cube root. The next topic after we deal with this is going to be like, okay, what if we have unlike radicals? How do we deal with those situations? Like if you have a square root times a cube root. That's the next place we'll go to. But I want to finish like radical things first. So let's say we have something like the square root of 6 divided by the square root of 2. Well, one thing that we could do is, because these are the same kind of radical, they're both square roots, I can go just put them both in the same radical. Just like how if we multiplied two square roots together, we can just take the numbers and put them under the same square root. Same thing's true with division. And then I can just worry about the 6 divided by 2 part, which is just 3. And I can't do anything more with the square root of 3, so I'm done. Right? The square root of 3, well, 3 is a prime number, so there's no perfect squares in it to worry about, so it's just done. That's not so bad, right? So let's say we have let's say we have 12 over 75, or square root 12 over square root 75. I'm going to start the same way. And I'm going to put them both under, or I'm going to put it all under the same radical. Because I noticed that there is, or 12 over 75 is reducible. Does anybody see how that reduces? If you're not sure, let's do a prime factorization, because if we have to reduce the radicals later on, that's probably also going to be useful to us. So we can like double use that. 12 is 2 squared times 3. 75 is 3 times 5 squared. Again, I drew, if you couldn't do that in your head, which, again, most of us probably can't. I've been doing it for 30 years. That's why I'm able to do it. Is you can draw the factor tree like we had done before, right? Now, if we have it written in a prime factorization, what can reduce? The 3's. Yeah, exactly. Just like from last chapter. So I'm left with 2 squared over 5 squared. So if I break the radical again, the square root of 2 squared is 2, and the square root of 5 squared is 5. So there's that. How's that? Still doing okay? All right. Let's do So let's say we have square root 10 over square root 63. So again, there might be some reducing that can happen between 10 and 63. So let's put it all under the same radical. Yes, sir. Sure. Again, does anybody notice any reducing between 10 and 63 as it's currently written? If you don't, we should do a prime factorization, and that'll tell us for sure. So 10 is 2 times 5, and 63 is 3 squared times 7. So no, there's no reducing that can happen, right? So this was kind of a wasted step, but that's okay, right? We didn't, if you couldn't look at it and tell there was no reducing to do in the fraction, then it wasn't wasted, and we're going to need the prime factorization anyways to kind of continue. So it's fine to have done that. Everybody's okay? I just want to point out that like putting it all into one radical didn't help us any, because there's no reducing that could happen here. But that's okay. Like, we didn't know that when we started, and that can certainly happen. So I'm going to go ahead and re-separate them. And now 3 squared, that can just turn into a 3 out front. And a square root 7 is still left in the bottom. Again, I skipped kind of writing out all the nitty-gritty details on that step. Is everybody still okay with what I did there? Okay. Again, if I skip too much and you're not sure what I did or why I was doing something or how I did it or why it was okay to do it, speak up and we can fill in some more detail and kind of flush some of that stuff out and more, But at some point we want to be able to like move from showing every single little itty nitty gritty detail like we did the first day into a little bit more compact work where we understand some of the things that we're kind of just shuffling through. So we're showing enough work for you're like, okay, I can kind of fill in the places in between here where I'm not doing like a tremendous amount of stuff and just going straight to the answer, doing it like all in my head, right? So I'm showing enough work to give some like milestones to the reader, but not so much work as it's like every single little tiny itty nitty gritty thing. Okay, so that's all the reducing that I can do with the radicals, right? But this is not going to be the way that we leave our final answer. One of the conventions that we've agreed as mathematicians is that we're going to leave no radicals in the denominator. You guys might have remembered this convention from geometry last year, right? When you did sine, cosine, tangent stuff. You didn't leave any square roots in the denominator when you found those on triangles. You guys kind of remember doing that? Maybe. It was a long time ago if you don't. And it's just kind of like, I don't know, that maybe sounds familiar. I'll take your word for it. Okay, that's fair. It was a long time ago. So the idea here is what we want to do is we want to rationalize that denominator. That's the name for the step that I'm about to do. So what I'm going to do is I'm going to multiply the top and bottom of this fraction by square root 7. So this is me rationalizing the denominator. That's the name of that step that I'm doing. So square root 10 times square root 7 is square root 70. And square root 7 times square root 7 is just regular old 7. So I'd have like square root 70 over 21. And notice here that if you took this fraction and found the decimal for each of them, they're going to give you the exact same decimal. We haven't changed the value of that number at all. We just changed the way it looks. So it doesn't have the square root in the denominator anymore. But it's still the same number. Is everybody okay with that? Just like when we make a common denominator for a fraction, like 1/2 and 2/4 are different fractions, but they're both the same number. They both are 0.5, right? Same thing here. Square root 10 over 3, square root 7, and square root 70 over 21 are different fractions, but they're still the same number. If you computed the decimal, you're going to get the same value. Whatever that value is, I don't know off the top of my head. It's going to be something less than 1. Is that okay? Let's do another. Kind of like that. Although you guys, I'm sure, have rationalized denominators before. I'm sure it's been a bit since we've had to do it, so let's not take that for granted, right? All right, let's say we have square root 30 over square root 108. Here, if you look at this, there's definitely reducing that can happen, right? Because 30 and 108 are both even, so I know that I can do some kind of simplifying here, right? Everybody buy that? All right. So let's go ahead and put them into the same fraction. And then we'll do our prime factorizations. (108) is, what is that? That's got to be 2 squared, and then 3 to the third. 27 times 4 is 108, yes. Okay. Oops, forgot to draw the radical in. There we go. Okay, so then we'll reduce, right? Everybody happy with that? What can we reduce? Well, I can do that, right? And I can do that. Everybody agree? Okay, so that'll reduce our fraction. That'll be 5 over 2 times 3 squared. And then what do? We radicals. So square root 5 over square root 2 times 3 squared. The 3 squared inside that radical can reduce, right? So we have 3 on the outside, and the square root 2 is left there. And that square root 5 is still left up top. Everybody so far so good? And then we have to rationalize our denominator. So what do I need to multiply here to rationalize this denominator? Anybody? So it's only going to be square root 2. Because the only thing I need to get out of the denominator is the square root part, right? So I'm just going to do square root 2. So that gives me square root 10, and then 3 times on the bottom, or square root 10 over 6. Yes, sir?
When you canceled out the exponents,
You're talking back here?
yeah.
Okay.
When you did 3 and then the 3, how come I made it as 2?
Because I only took away 1, 3 from the numerator. Right, the numerator has 1, 3. The denominator has 3 3s. I can cancel 1, 3 from the top and bottom, leaving with 2 3s on the bottom.
So then the 2 goes into the 2. That cancels out fully.
So I have 1 2 on top, 2 2s on bottom. So 1 2 from each leaves me 1 2 left on the bottom. Right? Remember, the exponent is just the same thing as like 2 times 2, or 3 times 3 times 3, right?
Okay.
3 went and 1 2 went. Again, if you're confused on how to do that, write out the exponent, write it out as a multiplication, and then it's super easy if you don't see how to manipulate the exponent there. Does that make sense, Stefan?
Yeah.
Okay. What's up, Walt?
So I get what's the problem. Like for 108, why did you put 2 squared times 3 squared?
So
Is
it's
that equal to 108?
2 squared times 3 to the third is 108.
Oh.
So I did the prime factorization where I like drew the tree. I just did it in my head.
So do you have to do the exponent, or can you like do the whole like?
If you wanted to write it like this, that's perfectly fine. You don't need the exponent there. You just need it as a prime factorization, whether you write it as exponents or you write it just all out. Either is okay.
And then, why exactly did you do two, why did you times the top and bottom by 2?
You're talking square root 2 at this step. So we've agreed that as a final answer, we're going to leave no radicals in the denominator. We have a radical in the denominator of our answer. To get rid of that, I'm going to multiply the top and bottom by that radical, because square root 2 times square root 2 is square root 4, which reduces down to 2. Is that cool? Okay. Good questions. So, did anybody see something that we could have done differently that would have made this problem a little bit shorter? Here's the trick. At this step, what if I didn't reduce the 2's? What if I only reduced the 3? Why would have that been a good idea? Because when I rewrite it as separate radicals, and I reduce the radicals, I have no radical in my denominator. I don't even have to rationalize. And I'm done. So again, when you write the 2 radicals as one fraction, and you do your reducing, if you're getting rid of, in this case, like we're getting rid of a perfect square, maybe you think to yourself, maybe I don't really want to get rid of that perfect square. Maybe I don't do that reducing here and save myself having to rationalize this denominator later on. Now, it's not wrong if you do that reducing and you miss it. It's no big deal. Just add a rationalizing denominator step at the end. But like, I'm not about that life. If I see a shortcut and a way to make my life easier, I'm going to grab it and take that. You know, but again, this is not really anything more than like a missed opportunity. It's not like you're going to do the problem wrong if you miss that. You just missed the shortcut, which is not a big deal. You'll still arrive at the correct destination. Just took a little bit longer to get there. And sometimes life is about taking the scenic route, right? So, everybody okay with that idea, Walter?
I don't know if you already said this, but how can you put 2 squared and 3 squared in the exponent? Square root.
So I am talking about at this step doing something different to make the problem that made the problem a little bit shorter. Okay with that? Mm-hmm. So in this problem, we did all the reducing we could. So I did my prime factorization of 108, and then I did my reducing. I reduced a 2 from the top and bottom and reduced a 3 from the top or bottom. That left me here. Come in. Thanks. Domenico, for you. What I wanted to point out to you on this stuff that I wrote in the gray down here is, what if we didn't reduce the 2's? Notice that I could still reduce the 2's here. I just chose not to do it. And the advantage of doing that is that I still have in the denominator 2 perfect squares. I have square root 2, I have 2 squared, and I have 3 squared. So when I take the square root, or I reduce those that radical, I don't have an extra radical in the denominator anywhere to have to rationalize later on.
So if you actually cancel out the 2's, did you get a different answer than...
So if we look at where we did that in the first problem, we do get the exact same answer. It just took several steps longer to get there. So that's all I was talking about was an opportunity to cut some work or to shave some work off of it. Yeah, so same problem, just talking about like, hey, did anybody notice that if we did this and not reduce the fraction fully, that it actually made the radical part easier later on because we didn't have to rationalize. That's what I was pointing out. Is that okay? Yeah. Let's do some cube root problems like this because it gets a little bit, some parts are mostly the same, but there's some parts that are a little bit sneakier. Okay? So let's see, what letter am I on? E. Okay, so let's say we have the cube root of 10 over the cube root of 16. Well, just like before, let's go write it as a single fraction because this is one that we can reduce. And the reducing, you should be able to see what to do in your head, right? How does 10 and 16 reduce? Five over 8, right? That's one that we can probably do in our head. I didn't bother with the prime factorization there. You could if you wanted to. Not wrong to do that. But again, like in the interest of, not showing a trillion steps, I didn't really feel like we needed that one. You guys agree? And I noticed that, hey, cube root 8, 8's one of those perfect cubes we talked about last time, right? The cube root of 8 is just, so I'd be done. Cool. Like that wasn't a big deal. Oops, forgot my equal sign there. Everybody feel okay on that? Instead, though, we had, yes, sir. Sure. No. Let's do that. So let's say we have the cube root of 135 over the cube root of 16. Is that fraction going to reduce? I can tell by looking at it, it won't. Why can I tell that immediately? I know that 16 is a power of 2. 16 is 2 times 2 times 2 times 2. And 135 is an odd number, so it doesn't have a factor of 2 in it. So I know that there's going to be no reducing that can happen there. Now, if you try to reduce it, it's not wrong to do that. We're just kind of, writing some extra steps that we don't need. What I'm going to do instead is I'm just going to write the prime factorizations in separate fractions rather than writing it all in one fraction, since I know there's no reducing that can happen. Everybody okay there? So the numerator, we can reduce that radical to 3 cube root 5. Everybody okay there? The denominator, see if you can follow what I did here, is 2 cube root 2. Again, what I did here is I thought about 2 to the 4th as 2 to the third times 2. So the 2 to the third comes out, and I have the 2 left on the inside. Everybody's okay there? Notice that I'm left with a radical in my denominator. So I need to rationalize this radical, or rationalize this denominator. What should I multiply the top and bottom to rationalize this fraction? This is the part that's a little bit tricky with a non-square root, because it's not the cube root of 2. It's the cube root of 2 squared. Why 2 squared? Here I have 2 to the first. The second, when I put them together, I'm going to get a 2 to the third, which is what I need to reduce the radical. Do you guys see that? So we have to be a little bit careful with these cube roots. So 3 cube root 20 over 2 times 2. Is that okay with you guys? Let's do one more of these and we'll talk about addition and subtraction. So let's say we have so does anybody see if there's anything that divides or that any way to reduce 525 over 12? Who's not sure? Probably most of us, right? So let's do this. Let's do the prime factorization first, and then after we've written out the prime factorization, we can decide to put the radical over the whole thing or the radical, or just keep the radicals where they are, right? Because that'll probably be a good idea. 525 is 5 to the fourth. 12 is 2 squared times 3. So what do you think? One big radical or two separate? Two separate, right? Because there's nothing in common. There's no reducing. Done. Okay. So to reduce the radical in the numerator, I'm going to get a 5 on the outside, and then 1 5 still left on the inside, right? Oops. There's no reducing that we can do in the denominator, though, right? Because I don't have any packages of 3. So we'll need to rationalize that denominator. So what do I need to multiply the top and bottom of this fraction by? How many more 2's do I need? 1. Okay, how many more 3's do I need? 2. Everybody see that? Because that'll give me 2 to the third and 3 to the third in my denominator, which is what I need to get rid of the radical. And then if we just multiply stuff out, what's that? That's 90 over 6. Everybody okay here? Sure. Is that far? Is that what you needed or no? Oh, okay, the part in green there is what I did to the top and bottom. All right, you guys ready to add and subtract? Okay. So the key with adding and subtracting is we can only add and subtract if the radical parts are identical. So the radical parts are identical. So we just add the coefficients like we would for a variable.
Wait, are we adding inside square?
No! That part stays the same. Just the coefficients. So it's just like it is when we add variables, right? Like 3x plus 7x is 10x. We just treat the radical part like an x. So that we can do. What if we have something like this? We have nothing to do there, because the radical parts are different. Everybody's okay with that? So if you don't have the exact same number under the radical, we can't add them together. Or if I have this problem, again, nothing to do. Because if I look, this problem is a cube root 2. This part is a square root 2. Those are not identical because the radical part is different. So there's nothing to do there. Everybody's okay with that? You're like, oh, this is super easy, right? How about square root 2 plus square root 8? Can I do that? Yeah, I can. Wait a minute, Mr. Kulik. 2 and 8 are different numbers. You just told me that I can't do that. Well, not as it's currently written. But what if we reduce the square root of 8? Eight is 2 to the third. So this becomes square root 2 plus 2 square root 2. And aha! Now it is in a form that I can add them together. So 1 plus 2 is 3 square roots 2. So we have to be careful, right? At first glance, that didn't look like we could add those two together. However, if we reduce the radicals, like all of a sudden this becomes a problem that's doable. So you got to make sure that we reduce radicals before we decide whether this is a go or no go. But that's basically the gist of it. Let's do just a couple more to make sure, and then we'll be done here for today. Sound good? Cool beans. All right. Yes. Yes. Okay. Let's say we have the cube root of 108 plus the cube root 500 minus the cube root of, or I'm sorry, minus 4 times the cube root 4. Well, I would start with prime factorizations because currently I can't add or subtract these, but, well, maybe I can after we change this around a little bit, right? 108 is 2 squared, 3 to the third. 500 is 2 squared times 5 to the third. And 4 is just 2 squared. So I just did the prime factorization. Again, if you can't do those in your head, which there's no reason that I would expect that you are able to do that in your head, you would just draw your factor trees. So if I take the first radical, I can reduce the 3 to the third. And the 2 squared, write as 4 that's left in there. In the second radical, I can reduce the 5 to the third, leaving just the 2 squared, but I'm going to write that as a 4. And then I still have that last one that there's nothing to do. That's just cube root 4. So 3 plus 5 is 8, minus 4 is 4. And that's it. What do you guys think with the adding and subtracting?
Could you do another one like that?
Yeah, where'd I lose you at on this one?
I just didn't see you left. I wasn't.
Okay. Okay. So we'll start by doing the prime factorizations. 40 is 2 to the third times 5. 525 is negative 1 times 5 to the fourth. And 135 is 3 to the third times 5. Oops. 3 to the third times 5. So far, so good? Okay. The first radical, the 2 can come out. So I have 2 times 3, cube root 5. The second radical, the negative 1 can come out. Right? The cube root of negative 1 is just negative 1. A 5 can come out. And I'm left with just 1 5 left in there. And then the last one, I have a 3 that can come out. So I have 3 times 6, and then still have the 5 left in. 2 times 3 is 6. And 3 times 6 is 18. So 6 minus 5 is 1, minus 18 more is negative 17 cube roots of 5. Cool?
Yeah.
Cool. Okay. I'm going to stop here. I'm going to get you guys an assignment here based on this stuff.